mainly it is used with GPU machines. In OpenMP, actually you can run the OpenMP even in desktop machines or your laptop and all. But to OpenACC programming, mainly it is meant for one of the programming language like CUDA and another one OpenACC. Both are meant for GPU machine where you can run the code. Part of the code will be run on your CPU host machine, and part of the code wherever you are introducing the parallel region or parallel code, it will be run on the GPU machine. So that is the main thing about OpenACC programming. So you cannot run your OpenACC programming in your ordinary desktop machines. Actually, we need the access to supercomputers or any other GPU machine so that you can run your code. So you know the difference between the GPU machine, where you have collections of processing units, they are equivalent to your CPU in your desktop machine or your ordinary laptop machine. We have collections of processing elements. Maybe thousands of processing elements, and they are going to use a common storage. It may be RAM and all. And we have a separate control logic for each of those. Here in the first row, we have collections of processing elements, which will be controlled by this control unit, which is given in this orange color blocks. Then they have their own cache memory, more number of different levels, cache level 1, level 2 and all. So it is as like private memory for these collections of processing elements. So nowadays we have GPU machine with 512 cores and all, and here it is the physical arrangement of our GPU machine, general purpose GPU machine, and you are writing your code in such a way that we start running the code in the ordinary host machine, which is CPU based machine. And whenever you have a parallel region in your serial code itself, we are introducing a parallel region. Only that part of the code will be loaded into the GPU machine along with the data. It may be a collections of voluminous information. So we load the data into the GPU memory. Then this part of the code alone will be executed by your GPU processing units, and rest of the code, once again after completing this part of the code, rest of the code will be again run on the host machine. So you might have heard this scenario when you see CUDA programming language. So we start running the code in the host machine, and wherever you have the parallel region, that will be loaded into all of the data will be pushed into the GPU memory. Then this part of the code, actually it is, we call it as a kernel code, that will be run on the GPU processing units, and once again the results sent back to your host machine. And for general purpose GPU machine, the following programming models are being used. So one category is low level programming, as like your CUDA programming, OpenCL, which is another language. CUDA programming it is like a framework. It support execution on GPU machine. OpenCL as like your language, almost equivalent to C programming construct. We have all the looping construct and all those things. It is like a language, but they are providing maximum flexibility for the programmer, because it is low level programming. We can directly interact with the processing units, the computational processor. We can actually we can assign which task to be assigned to which processing units and all. Such flexibility will be here. But OpenMP as well as OpenACC. OpenACC stands for accelerator. So both are having like a directive kind of things. As like your OpenMP, we have the parallel narrative, pragma. Then for directive. So as like our OpenMP, here also we have collections of directives. But for the programmer, when you consider the programmer here, the flexibility is for the programmer. We can simply write the parallel region. We will not worry about which part of the task or which parallel task assigned to which processing unit. All those things will be taken care by the system itself. So that is the main difference between CUDA programming and your OpenACC. So when you are writing the code in OpenACC, we have some higher level constructive directives. So we no need to worry about whether thread 0 will do this task or thread 1 will do this particular task and all. And all those things will be decided by the system itself. So OpenACC, actually it is equivalent to a programming standard, which is mostly designed for NVIDIA GPUs. CUDA will be mainly used for, I hope you might have attended the session for CUDA. So CUDA is mainly focused for Intel GPUs. OpenACC is meant for NVIDIA GPUs, and it will simplify the GPU programming because the end user, we no need to worry about the internal arrangements of the processing units, and we no need to worry about the memory, how it will be stored in the memory, GPU memory and all. So in the code itself, some special commands like directives are introduced, and that part of the code will be executed on the GPU processing units after we load the data into the GPU memory. And for OpenACC, we have a syntax both for C programming based, C and C++ programming based syntax for every directive, as well as we have Fortran language based directive for OpenACC directives. And it is supported across different platforms. And the ordinary compilers like your GCC can also be used to compile your code. But anyhow, you cannot run the code on your ordinary CPU machine. If you run the code in your CPU machine, and then you cannot interact with the GPU. So definitely we need the GPU processor and GPU machine to complete the execution of your OpenACC program. And how the task, here they are comparing CUDA programming GPU and NVIDIA GPU, how the arrangements of the processing units, and what about the logical view of the task or logical view of your threads. So in CUDA programming, the GPU device, we call it as CUDA grids, which have collections of blocks of processing units. And here in OpenACC, we call it as a kernel. And kernel and grids, it is physical arrangement of collections of blocks of processing units. And here the processing unit is known as streaming multiprocessor, SM, we call it as SM. And collections of SM will make a block. And in one block, we have collections of threads, CUDA threads. Here we call it as CUDA threads. And the threads, the collections of threads are assigned to your core, where the processing unit in the GPU machine. And normally in the logical view, we call it as a war, which is collections of threads. We make a group of threads. Usually the number of threads in the warp will be 32 threads. Now it is extended up to 64 threads in a warp, or 128 and all. And blocks are divided into collections of warps. And your SM, the streaming multiprocessor, which is the element, the processing element, the basic element in the GPU machine, will execute the threads in the warp. So that is the level of granularity. That is, we have collections of grids, collections of blocks, block in terms have collections of threads, and each of the thread will be executed in one SM, the processing multiprocess streaming multiprocessor. And these arrangements, it is as like your usage of what will be in your single user machine. We have the program instruction register. That is, it will have address of next instruction. In some system, we call it as, in some architecture, we call it as a program counter, or in some architecture, we call it as a instruction registers, which will give the flow, what will be the address of next instruction and on. It will decide the serial flow of your code. Next instruction address will be loaded into the program counter and all. So as like your control, program control or the instruction register control, here what will be the collections of threads will be the collections of threads will be given to the processing unit. So based on your machine, GPU machine, and sometimes we have two such control warps, two such control units, or 4, 8, and so on. And the number of threads in one warp is also being, it is starting from 32 threads to, it is now extended. Then in OpenACC task, where the equivalent to CUDA programming, here block we call it as gang, which is again in terms of collections of blocks, collections of threads arranged in blocks. And one warp means it is known as a worker, and vector will be equivalent to your threads. So in CUDA programming language, when you use the term, we have n number of threads. Here we say we have n number of vectors, and n number of vectors will make one warp or one worker, which is equivalent to collections of threads. Then collections of such a block of threads will make one gang, and so on. So the level of parallelism in OpenACC programming will be, so logically we see gang is a collections of threads which will going to do a particular task. Then in another level, the gang itself is split into collections of worker. Maybe it is warp 1, warp 2, or warp 3, and so on. Here we call it as a worker. In CUDA programming, we call it as a block. And gang is equivalent to your collections of threads. Again, it is divided into collections of workers. Then again, it is split into collections of multiple threads. And here it is known as vector. So vector is equivalent to a thread, which is a single flow of execution. Then sometimes if you are going to specify how many to run your OpenACC code, how many gang you need, and how many workers you need, and how many vectors per worker. How many vectors, a vector means now the thread, how many threads we need for one worker or one block. Those things can be explicitly specified in the directive itself. So it is the syntax used for C programming code. So in the first line, the pragma, it is equivalent to the directive structure is equivalent to OpenMP. So we start with every parallel region using as pragma, and it is OpenACC. So it has the keyword ACC. Then kernels. Then we have how many gangs we are going to create. To do the corresponding, the following parallel loop, how many gangs we are going to create, and how many workers per gang, then how many vectors per worker we are going to create. So we have two syntax, one for C programming and another one for Fortran programming. And here we have two different directives. We will see these two directives in detail. Kernel is one directive structure and parallel is another major category. This two will be the major category in the OpenACC programming. So if you use this directive, then it is the syntax to be used. If you are going to use parallel directive, then this is the syntax. Similarly, for Fortran, this directive, always it will start with this exclamatory symbol, then $ACC, then your kernel directive or else parallel directive, and for each case we have the corresponding syntax. So gang will say how many gangs will be there in the particular parallel region we are going to create, and workers will say how many workers we are going to have per gang. Then vector length will say how many threads you will have per worker, right? So if you want, you can explicitly specify these things, or else you no need to specify these structures, how many workers you need, how many vectors you need and all. And based on the availability of the processing unit, the system itself will decide all those things. But it is one way of having our own control over how many gang or workers or vectors we need to be created. And here the idea is total number of threads created or total number of vectors created will be, it is as like gang is equivalent to grid in your CUDA programming language. So one gang will have so many workers, and one worker will have k number of vectors or k number of threads. So the total number of threads created will be n into m into k, right? Number of threads to do the parallel region will be n gangs, each having m workers, and each in turn having k number of threads. So the total will be n into m into k. Sir, is it okay for the participants?
Yes, madam. It's going.
So far,
yes, madam. It's comfortable.
Because OpenACC, we cannot go for the practice kind of things. So we need the GPU machine access. So that's why I'm giving only the examples and the coding part, right?
Participants,
here,
please post questions. If you have any questions, I'll be helping madam to address the questions.
So if you have any queries and all, you can post it. So as we have seen, threads is equivalent to your vector, and the individual tasks that are executed on the GPU processing unit will be now known as vectors. And these vectors are organized into warp, and how many warps at a time, how many warp you have and parallelly you can run, that will decide your parallelism, level of parallelism. So almost minimum 2 warps will be there, and all the threads within a warp will be assigned to one GPU core. So it is equivalent to, we are feed the parallel code to the corresponding GPU core or GPU processing units. And now this group of threads are scheduled and executed on this GPU core. And as usually, you know, compiler directive, because already we have seen OpenMP. So we see the purpose of this directive to create a parallel region. And here we have the following directives to create the parallel region, parallel code. Then here we need to move the data from host machine to GPU machine. Similarly, the result must be sent back to your host machine CPU. So we have appropriate directives to copy the data from host machine to GPU. Similarly, GPU to host machine. And the basic directive, it starts with the Pragma, ACC, and the name of the directive followed by collections of class, like as like for OpenMP, the syntax is almost equivalent to OpenMP. So here the name of the directive will be there. In Fortran language, we have the same syntax, but it starts with this key exclamatory symbol, a $sign ACC. And every parallel region will be ended using a separate end directive here. And here we concentrate only on a C programming based OpenACC syntax. And you know the meaning of these things. Once the compiler, while doing the compilation, once it see this line has pragma, it will know it is a parallel region, and it will give the instruction to the compiler. The following code must be executed using OpenACC. Actually, that code, that part of the code must be run on a parallel GPU machine. And classes, we have some specifiers like your as like your private or shared data or your copy in those specifiers and all we can include as classes in the directive itself. And the execution model, ordinary C program, you are running the code in your GPU machine. And once you reach this parallel region, this green color region indicates the parallel region. And now the control is given to your GPU machine. This part of the code will be run on your GPU processing units. So only usually the IO operations and all will be restricted. They will be done on the CPU machine only, because your GPU is mainly used for doing the computational tasks, highly intensive kind of work. So only for that purpose we are using GPU machine. So normally we will not do any IO operation on that particular GPU machine. So you start with the serial program, your application, and where you get the data, collections of informations and all. And these things will be run on the ordinary host machine CPUs. Then your data will be moved to the GPU memory. Then you start the execution of this parallel region on the GPU machine, and result will be sent back to your host machine again. Even 5% of the work, if you parallelize using GPU machine, it will improve the overall performance of your work. And the compilation command, if you are using C programming code, we use the PG GCC to compile your code. And for C++, we are going to use your compiler GC++. For Fortran, we use PG Fortran compiler. And that is what I told earlier. Every OpenACC directive, wherever we need parallelism, we have two different approaches for defining the parallel region. One directive is using kernel. Kernel is one directive. Another one is parallel. So in OpenMP, we have only the parallel directive. But here we have two different category. The reason is one parallel directive where the programmer has to do every planning, low level planning and all. And in another option, the programmer no need to do the low level planning and all. The compiler, we are saying the following code must be executed in the GPU machine in parallel on the parallel machine. So the compiler will take care of doing all the work, mapping the task to the corresponding GPU core, and all those things will be taken care by the compiler itself. So both a directive where we are defining a region, which is we call it as a parallel code. that will be executed only on the accelerator, only on the GPU machine. And sometimes we can have collections of such a parallel region in your C programming code itself. And here work sharing inside a kernel, we can have multiple nesting of kernels also allowed. So we can go for particular task alone, we can create another kernel, another parallel region. Like that, we can go for nesting also. But in parallel directive, the work parallelism must be defined by the programmer. The low-level planning must be done by the programmer, but in kernel, it will be done by the compiler. But when you see the performance-wise, both will do well. So here will be example, kernel directive, pragma kernel. So the following for loop we are going to parallelize. So we enclose this part of the code within the pragma kernel directive, OpenACC kernel directive. So here we will not say how many threads to be created and how many gangs or how many vectors are needed and all. Simply you say the following region of code is a parallel code that must run on your GPU machine. And here the compiler will take care of, it will assign the work to the corresponding processing units, create the gang workers and vectors and all. So this example, where host machine will start the execution of this code. So we are initializing this array. Then once you store the array with the elements, we are creating the parallel region using kernel directive. Only this part of the code will be run on the open, actually it is the OpenACC parallel region. It will be run on your GPU machine. So now kernel is equivalent to a programming module which will be executed in parallel in the GPU processing units. It is in CUDA also you might have heard this word kernel. It is the code which will be run on the CUDA processing unit. So here it is a parallel region which will be, so in CUDA programming you write a separate function or separate method and namely kernel code. And wherever needed we call that kernel code. That code will be run on the GPU machine. Here we write the parallel code within one directive itself. So once you reach this parallel directive, this part of the code will be run on the GPU machine, right? So it is one example, and here we are simply adding. We are doing some computational task on the individual elements of array A. So we will not, for simplicity, we take A of I is updated with addition 1. We add one data 1 to every A of I. And here, for simplicity, we are printing only A of 0. And it is another example where we are going to compute this A into X plus Y, where X and Y will be vectors. We have thousands of elements in X or thousands. Usually we go for GPU programming when you have a large volume of information to be processed. Otherwise, it is enough to use your OpenMP itself, right? So your X and Y will be a vector which have thousands of elements or 10,000s of elements, where we are going to apply this computational work, multiplication and addition. So the data, we start with the ordinary C program, n equal to 1000. Then we are creating this array X and Y, because we cannot go for such a voluminous IO operations. 1000 iterations we cannot do. So we initialize simply X of I and Y of I with some initial value, floating point values. Then we start the parallel region. Now these X and Y they are available. And here in CUDA programming, we use separate memory copy functions, right? I hope CUDA programming is over, right, sir? Sir?
Madam, Coda program is tomorrow. There is a session on Coda programming, madam.
Oh, okay. So when you write the code in CUDA programming, actually it is low level programming. So we have to explicitly copy this array X and Y in the GPU memory. Then the GPU will access those things and result will be once again explicitly transferred to your host machine, a host CPU machine. But here everything will be done by the compiler itself. So it is as a programmer, it is easy to write OpenACC program. Wherever we need parallelization, wherever we have a code which will be run on the GPU machine, then we can introduce one parallel region as like your kernel, pragma and kernel. And no need to specify how many threads are needed and how many workers are needed and all. And now if you are running this code, compiling this code, you will get such kind of message. As I told, this X and Y, actually it is available in the host memory. Host memory means it is in the CPU memory, CPU machine memory. So it will be pushed into the GPU memory. So that's why we get this while compiling the code itself, we will get such messages. We are creating copy in will be like moving the data to feeding the data to GPU memory, GPU machine. Then we are here we need array X, collections of elements available in X, then collections of elements available in Y. And once again, after you modify the data, X of Y is multiplied with A, then added with Y. Then it is again updated in Y of I itself, right? X of I multiplied by one scalar value A, then it is added with the Y of I, then it is the result will be updated in Y of I itself. So now your Y will be as like it is what input array, and once again the result is also available in the array Y. So it is like the input array as well as output array. But when you see X is like only input for the GPU machine. So that's why you will get this message generating X copy in of X. So it is saying we are creating X is like input to the GPU machine. So in the GPU memory, we are creating an array of size 1000 elements, the name X. So it is a copy in operation. Then we are generating on the GPU machine, we are generating one array, namely Y with 1000 elements, which will be acting as both input parameter as well as output parameter. So simply we have copy, we get the messages copy. If it is only data transfer from host machine to GPU machine, we will get this message copy in. Now Y must be first copied into the GPU machine, GPU memory. Then once again it must be copied back to, after update, it must be copied back to the host memory, host CPU memory. So we get this message, copy of Y. An array of Y is created on the GPU machine. Then when you reach the statement number 19, it is parallelizable loop. Now the kernel code is generated. So this part of the code is now equivalent to as like a function, kernel function in your CUDA programming. This parallel region code is generated. Then it start the execution using, because here we will not say how many vectors are needed, how many threads are needed, and how many guns are needed. So it will be decided by the system itself based on the size of your data to be operated, and based on the availability of processing unit in your GPU machine. So here 128 threads have been created. So while compiling the code itself, you come across all those messages. These are all the messages generated by the compiler while executing the main function. And this line indicates this code will be run on the kernel. The kernel code is run on the GPU machine. And the keyword copy and copy in, as I have already told, it is for showing the data transfer from host machine to GPU, GPU to host machine. Dear participants, do you have any queries to this? But actually, the work must be submitted to the GPU machine. Work is actually submitted to the GPU machine, right? Then we see the difference between, there is, I have told another directive, parallel directive. Now we have seen the kernel directive, and another example is parallel directive. So here, it is the duty of the programmer to identify which part of the code can be done in parallel, and we have to explicitly generate the kernel code. And here, when you go for kernel directive, and it will see whether you are creating the parallel region, and now the OS will decide which part of the code you could run in parallel. Only that part of the code will be done on the GPU machine. It will see the for loop and come to the conclusion. We have some scope for parallelization here. So this part of the code could be run on the GPU machine, and it will create the kernel code and push the data into the GPU machine and all. But if you use parallel directive, it is the syntax for creating a parallel region using the pragma parallel directive. And now this for loop, whichever loop to be parallelized, it must be identified by the programmer itself. Then it will create the kernel code. And now, if you create parallel region using kernel, it is more implicit, and the compiler have freedom to create a number of vectors and number of workers and gang, and map the task to the individual processing elements, and all the freedom is given to the compiler. So the programmer no need to worry about all those things. And the compiler performance, it will do all the analysis. It will analyze the code, and it will parallelize. And it will see whether it is safe to parallelize the code. Then it will go for parallelization. But if you use parallel directive, then here it is the duty of the programmer to ensure that that particular for loop is safe to parallelization. That particular looping construct is safe to run on the GPU machine. And those things, those analysis must be done by the programmer. So he has to analyze the particular code, part of the code, and he has to verify whether it is safe to run the code on the GPU machine, because it involves lot of data movement from host machine to GPU machine and all. But the data movement is done implicitly, both in kernel directive as well as in parallel directive. The data movement is done implicitly, right? So that's what the difference between kernel and parallel loop directive. So kernel will just give the hint. There is a chance, there is a part of the code which would be parallelized, and the kernel, the compiler, it has to identify that particular code and verify whether it is safe to parallelize the code and all. But if you use parallel loop directive, and where the compiler will not do all those analysis, it will simply compile the code, translate the code, whichever is marked inside the parallel region, and it will not ensure that it will not see whether it is safety to parallelize the code and all. That analysis and that thing will not be done by the compiler if you use parallel loop directive. So it is the duty of the user or the programmer to ensure that, right? So an example, pragma kernel directive and another one parallel directive. And inside the parallel directive, we can have as many loops. Another directive, which are actually loop is not a separate directive, but inside a parallel region, we can include the directive, namely loop. So this loop directive should be used only within a parallel region. So wherever you have a for loop which could be parallelized, then we can create a separate directive using loop. So now inside the parallel region, we have two separate parallel loop. So the idea is these two parallel loops. Before going for this one, we see the data dependency. That is also important thing before you write this code. In OpenMP itself, we have seen the data dependency, right? When we are going to parallelize a for loop, we need to ensure that there should not be any data dependency. Here, the first example, every x of I will be generated using the adjacent element x of I plus 1. You have collections of elements stored in array x, but every x of I manipulation involves x of I plus 1 or else x of I minus 1. So we have data dependency across the loop iterations. The loop iteration x of I depends upon x of I plus 1, or else the loop iteration x of I plus 1 depends upon x of I. So across the loop iteration, we have data dependency. Such for loops cannot be parallelized. Now, if we are using the pragma kernel based parallel region, if you are using the kernel based parallel region and we put one for loop like this, and now the compiler will know, because in parallel region created by the kernel, it is duty of the compiler to decide whether it is safe to run the code in GPU machine in parallel. So now the compiler will see this code. So it will see the data dependency and conclude that this code could not be done in a parallel machine in a parallelized way. So as usual, this for loop will be executed in the host machine itself, even though you are using a pragma kernel region. Since this for loop has a data dependency, the compiler will make the decision. So it will not push the code into, it will not create the kernel code. It will not push the code or data into the GPU machine. This part of the code will be run on the host machine itself as like a serial code. But it will give such error messages like warning or messages. In statement number 14, we have data loop carried data dependency across the loop iterations. So it prevents the data parallelization. Right? But if you use pragma, this one, the parallel directive, then you will come up with the error wrong outcome and all, right? So here the compiler will analyze the code and you will get such a warning or error messages and all. So it will analyze for data dependency, then generate the kernel code. If there is no data dependency, it will run the code in the GPU machine, or else the code will be run on the host machine itself. and it will take care of copying the data to GPU machine. Similarly, it will take care of copy out the resultant data from the GPU memory to CPU and release the memory in the GPU machine and all. So all those things will be done by the compiler during runtime. So that is what the data dependency. Now, if you go for this parallel directive, we are writing inside the parallel region. We have to ensure that there is no data dependency in this for loop. There is no data dependency in this for loop. Then we have to create, it is possible to create separate parallel regions inside this parallel directive. So the thing is, there should not be any data dependency. Sometimes the second for loop will be executed before the first for loop, right? Can you follow this? If it is inside the kernel region, then they will be executed only in this order. So it will generate two kernel code, one for the first for loop, another one for the second for loop. But the second for loop will always starts only after the completion of first one. So here, if it is a kernel directive, the compiler will decide this. So the first for loop will be executed followed by second for loop. In parallel directive, we are creating inside the parallel region, we are using a OpenACC loop directive. It will say this for loop can be treated as a separate kernel, independent kernel, and this for loop can be treated as a separate independent kernel. Sometimes this kernel will get the processing unit first before the first one, but it will not affect the overall outcome. So there is no barrier point between these two. These two may be run in parallel. Sometimes this will be run on a collections of processing units in the GPU machine. At the same point of time, this for loop, this modification will be done on the same GPU machine in parallel, or else first this for loop can be completed before this one, right? And what are the other classes that would be included in the parallel directive? It is just like your OpenMP, right? So one of the option is if class. In OpenMP also we have if class. The outcome of this condition will decide whether the code to be run on accelerator, GPU machine or host machine itself based on the outcome of this if condition. Then asynchronous class. So the following parallel code must be run in an asynchronous way. Then number of gangs, that one already we have seen. We can explicitly say how many gangs to be created to run the code. Then number of workers per gang, number of vectors per worker, vector length class, then private class, as like your OpenMP. What are the variables that will be accessed, that will be used or treated as a private member inside the parallel region? That private class, a set of variables with comma separated variables. And first private also equivalent to OpenMP code. So initially it will take the data already available before you start the execution of the parallel region in GPU machine. They will be as like initializing those things. They take the initial value from the main function. Then afterwards, whatever the data update done on those things will not be directly visible to the host. So it is also similar to OpenMP. Reduction class is also available. So here to update one data, there is a private reduction class already we have seen. If you want to update a data in a mutually exclusive way, then we can go for reduction. And again, we have some restriction, only some of the operations that can be done using reduction class. And when you say reduction class, for every thread, a separate private copy of those variables will be created. And finally, those private copies are made available into final result. And that will be available to the host machine, your CPU machine. So it is execution is as like a OpenMP code. Reduction class. So here one example, we are creating a parallel loop with a max variable, variable name dt, and the operation we are going to do is max on that variable dt. We have to find the max value. So two for loops are there, and we do some update, like we are subtracting, and whichever value is maximum, here we do some update on elements a of I, the matrix elements a and u, and whichever is maximum, dt is initially taken as 0, then the new value is generated, it is compared with the dt, and which is maximum, that is taken as new dt. So now for every iteration, there will be a private member created with the name dt. Then once it is reduction operator, so without using any other critical section code and all, this dt will be updated in your overall answer. Right? So these things, why we go for the critical section code and all, you know. So even if you ignore this one, in OpenACC, the kernel, that compiler itself is smart enough to create this variable as a reduction operator, even if you ignore this one. But if you want, you can include this, right? But such flexibility is here, because OpenACC, the programmer may no need to do this such kind of low level options or low level programming. Even if you ignore this, this task will be internally done using reduction option only. Every thread or every vector will have its own dt that will be updated in the overall global dt. So these are all the classes that would be included in parallel and kernel directive. This one already we have seen. So we have small changes if you use kernel directive or parallel directive. Only the keyword is changed. Then another option is data directive. So already we have seen when you create a parallel region, the data will be explicitly moved from your host machine to GPU machine, and result will be moved back to your host machine implicitly. But sometimes we have another directive, namely data directive, which is providing such option. We can create an array of data x and y, and we can say which must be input for the GPU parallel code, which will be the outcome from the GPU parallel code. Such option could also be included in the directive, data directive. So here the programmer, we have the control over which part of the code must be moved to the kernel through kernel, which part of the data to be moved to the GPU memory, and which part of the result to be moved back to the host memory. We have such control over such data movements if we use explicit directive, namely data directive, right? So we have the following classes in the directive: data directive, as usual if condition, and outcome of this condition will decide whether the data movement must be done explicitly or not. And copy in, this list will be equivalent to giving input to the GPU machine. Copy in is equivalent to we are transferring the data to GPU machine, and here the memory will be assigned in the GPU memory. Then the data will be copied into the GPU machine, GPU memory. Then copy out will say it is the outcome of after running the parallel code in accelerator. What is the outcome of that parallel region? That is like output from the parallel region, copy out. Then copy stands for this list of parameters will act as both input to the GPU memory, GPU machine, as well as it is acting as like a output to the output from the GPU machine to host machine. So there is no explicit in or out. Then create, it is to create the following variables or the following data in the GPU memory. It is to create the following data, or explicitly we are going to allocate memory in the GPU memory, and we are creating those things. Then present. So sometimes you are saying we have to create this. If it is already present, the GPU memory, that will be taken. So we see the option one by one. Copy list. It is doing both the data movement. Memory, it allocate memory on GPU machine. Copy the data from host machine to GPU memory. Once you reach the parallel region, then before starting the execution of the parallel kernel, it will do this. Then once you exit from the region, the data will be copied back to host memory. Copy in is as like input to the GPU memory. So it allocate memory on the GPU and copy the data from host to GPU memory. Once while starting the execution of the parallel region, this copy in will take place. Then copy out, when you exit from the parallel region, the outcome, whatever the data generated by the GPU machine, is copied back to host. Then create list, it is allocating memory explicitly on the GPU machine, but it is as like no data movement, but we are doing data memory allocation alone. So it is as like we are creating some temporary memory or temporary variables in the GPU machine. And this block of memory could be used by the parallel region, but no initial data in that particular block. Similarly, that block of memory will be used temporarily while executing the parallel region, and no data movement from the block to the host machine. Then present is, it will say the following list of variables or data already present on the GPU machine. If it is already present on the GPU machine, then they will be used. That's all. Otherwise, if it is not present, it is equivalent to create. If it is already not present in the GPU machine, it is equivalent to create. So in the GPU memory also, they take the same name. In the host machine, you are using the array name X and Y. On the GPU memory also, they take the same variable name X, Y, etc. Right? And the syntax for C programming is creating a directive for doing data copy. It is explicitly we are doing this. So the following array A will be acting as like input and output. Array B will be input for the GPU memory. Array C will be output from the GPU memory to host memory, and created D, a block of memory with the name D is created on the GPU memory. And present is, if it is already available, then it will make use of it. If not available, it is going to create. So we need to have both create and present, because sometimes you might have already created the array with the name D in the GPU memory. So if it is present, it will be used. Otherwise, it will be created as a new block of memory in the GPU machine. But it is used as temporary memory for doing some processing while running the parallel code, right? Then for Fortran language, it is the syntax being used. And this one example along with the data directive. So it is the serial code, as usual, the serial code. And now we are going to introduce the parallel directive, parallel loop directive. Then we are giving the options. First, we start with the data directive. And what are the things to be fed into the GPU memory? A and B input variable, and result will be the output from the GPU memory. Then we are creating the parallel loop. Now it will be include the option present, and it will verify whether AB already present, result and all already available in the GPU memory. Then this for loop will be executed by the GPU processing units in parallel. And now explicitly the result, because we say result is copy out, it will be moved back to the host machine memory. So this for loop, only this parallel region will be executed in the on the GPU machine, and this for loop will be executed by the host machine itself. It is IO operation. The result available in the host machine memory with the same name, so it will be just printed. But in if you are going to use CUDA programming and all, we need to explicitly do the data memory allocation. We have a separate function to allocate memory in the GPU machine. Then we have to do the copy in. Here, the copy in itself will take care of allocating memory in the GPU machine itself. All right. And another example, we are creating a data directive. Inside this, we are copying, that is, we use copy. So A, B, C, all three will be acting as input as well as output. So whatever the modification done on A and B will be available in the host machine again. And we are creating the parallel region. And now this part of the loop will be executed in the GPU accelerator, and result will be available in your host machine with the same name, vector C. All right. So with this, we come to the end of the session. So here in OpenACC, writing the program is very simple. We are creating the parallel region wherever we have the code which could be run on the GPU machine. We have two category of creating parallel region. One is the kernel, another one is the parallel directive. Each of them, they have their own advantages and disadvantages. And if you use parallel or kernel directive, the data copy from host machine to your GPU machine, and GPU machine to host machine will be implicitly done at the beginning of the parallel region as well as the end of the parallel region. Sometimes, if the programmer need to control this, which part of the data alone should be copied into the GPU memory, which part of the data to be copied back to your host memory, especially when you are using parallel directive, the programmer has to decide all those things. So we have data directive with the following classes, right? But anyhow, to compile your code, it is we have to use the slum code. We have to access the GPU machine, right? Participants, do you have any queries in this? Sir?
Dear participants, if you have any queries, you can just put them in the chat box. No.
Okay, tomorrow if you see the CUDA programming, then you can relate both the OpenACC and CUDA, how it is different from, because CUDA is low-level programming. So we have the syntax itself, we have to say how many threads to be created, how many blocks to be created, how many grids to be created. And now you can compare both OpenACC and CUDA programming. So OpenACC is something like your high-level language, and that one is equivalent to your low-level programming code. CUDA program. Right?
Dear participants, if you don't have questions, then let us try to conclude. So if you have any questions, you can just post in the chat box.
Sir, are they having access to the supercomputer? Are we providing any?
No, we are not providing any such resources, madam.
Okay.
We are not providing any.
Such
But
facilities.
if anybody approaches, then we'll try to help them.
Yes,
how
sir.
to
Yes,
get
sir.
it. So since I did not find any questions, madam,
Okay, sir.
so let me take opportunity to share the end remarks on the session. Once again, good evening, all the participants and the esteemed speaker of the today's session. Madam, so
Sir.
the session is more informative on OpenACC, and I would like to take a moment to reflect the value and potential this technology holds for all of us.
Yes, sir.
Over the course of this session, you have made us to explore how OpenACC simplifies parallel programming, accelerates computing, and enable innovation in various applications, as you said. And we have also shared the insights how this OpenACC will help them to solve the parallel programming, and the insights and then tools shared in our sessions are really helpful to practice the sessions. I encourage each of the participants to continue exploring the OpenACC, apply the knowledge gained through the session, and you can apply in our projects too. A special thanks to Devi Mahalakshmi madam for her facilitation to the participants, sharing her expertise in the OpenACC. Madam also took one session. So this is the second session. Madam is very enthusiastic and such an open mind person sharing the knowledge. And let's carry forward the momentum from this particular session into our HPC work. Could it be regular and then research work?
Yes, sir.
So thank you all once again, and I wish you a success in all your future efforts in the HPC. And I thank you very much, madam, personally
Thank you,
on
sir.
behalf of our institution, Chaitanya Bharati Institute of Technology, the Department of IT, and particularly from the organizing team and our faculty members. And on behalf of the entire participants, I once again extend my heartfelt thanks to you, madam. Thanks
Thank
for
you,
sharing
sir.
your valuable knowledge with us in OpenACC session. Thank you very much, madam.
Thank you, sir. I'm also very happy to be part of this FTP. Even though it
Yes,
is
madam.
online session, even we are planning to visit your college if the FTP is offline. Yeah,
Yes, madam. We are
visit your
planning
campus.
offline session in summer, madam.
Yes.
Probably we'll have one